This session is dealing with the geometric dimensioning and tolerancing. Um, in the last topic, we talked just with tolerancing. Those are numbers. Um, yeah, any type of tolerancing, you're dealing with numbers, but this is dealing more with the geometric dimensioning, using the geometry of the part. What I'm showing you here is a way to dimension a part, put tolerance on it. You got your side view, got your front view. We've got a tolerance on a hole. Um, we've got a tolerance here on a counter bore and how deep, two places. You have, this is in millimeter, obviously, 55 millimeters long. It's got a tolerance on the width. But the question is, I mean, you can still build this part. The question is, how can you inspect the part? Is there certain datums? Is there a hole pattern? Um, So there's no geometry. They're not calling out how flat they want that. I'm assuming anything that's not here would be in the title block that you would have to read to figure out. All right, because not everything is on the drawing. A lot of things are in the title block. All right, such as all dimensions in millimeters, angles plus or minus. I think that looks like 5 degrees, and then dimensions are plus or minus a half a millimeter. All right, so this one here, 55, would be plus or minus half a millimeter because it does not take on. See, this has its own specific range right there. There's the tolerance. Just like the diameter of the hole, it's 8.4, 8.0. It does not pick up the tolerance here in the title block. But the ones that do not have it, like 55, the radius 4 would have one. But everything else looks like it's got its own tolerance. So let's look at the next page. Now this one here has GD&T. All right, and all they are symbols for manufacturing the part, for building it, but not just building it, but inspecting. So here they're showing what datum A is. This is datum A. See the Hershey Kiss here. They're saying that this surface right here is datum A, and they're calling out the flatness of that surface. It'd be 0.25 millimeter. So we'd have to check the flatness. They're also checking the straightness of it. This is a symbol for straightness. All right, and they're checking it at, you guys should understand that symbol, that's MMC. Okay, so the part, when it's at its MMC condition, needs to be 0.25 straight. Look at the other view. There's datum B. Usually datum A is the longest, biggest side. Datum B is the long edge. And then datum C is the short edge. So you have a 3-point contact on A, 2-point contact on B, 1-point contact on C. So you got your primary, you got your secondary, and you got your tertiary datums. Notice there's dimensions that have boxes around them. All right. These are theoretically exact. These are called basic size. They're theoretically exact. We're not checking 10 or 10 or 35, but we're using the true position. Okay, this whole thing right here, we're checking the part, the whole pattern, true position, and it has a 0.7 positional dimensional tolerance at MMC, and the part has to be within datum A, B, and C. All right. And of course, the hole has to have a certain size. If the hole didn't have that size, then the part would not be inspect. And they're doing the same thing with the counter bore. Here's the counter bore symbol, the diameter. It has a depth of 2.6 to 2.0 deep on the counter bore. But they're looking at the true position from datum A, B, and C of the counter bore as well. So those are some of the GD&T. There's another one I want to show you. Here's this one. So here's a basic part. There's no GD&T. Part can be made, but there's no datums. There's no, how am I going to inspect it? There's no flatness call out. There's no perpendicularity or parallelism. So again, this is the old method, and using GD&T should be on the next page. There's the GD&T for this one. See? So let's look at datum A. Datum A is right here. There's datum A. So the part would sit on datum A as it's being inspected. They're checking the flatness, okay, of 2/1000ths. So they would run, they would do a flatness check on that. How do we check these? Well, you can use hard gauges, but you have to establish a hard gauge. Or you can use a coordinate measuring machine, which most people are doing nowadays. Those are becoming very popular for checking for GD&T. Let's look at some other ones. Where's datum B? Datum B looks like it's on this shaft right there, that diameter. So datum B is there, and datum C is this bore diameter. So you got A, B, and C. Looks like there's no other datums. So let's look at here. This is the runout symbol. All right, the runout symbol, and it has to be within 1/1000th from datum B. So which means they're going to chuck it up on datum B right here as they inspect the runout of that bore. But the bore has to be within the size, 980 plus 5/1000ths minus nothing. Here's a parallel, okay, parallel call out. It has to be on datum A, so they put the part on datum A, and it has to be within 3/1000ths parallel. Here's a true position, another true position, perpendicularity. All right, so they're looking at this bore down the middle. It needs to be perpendicular to A, which is this face here, so it makes sense. We'll look over here. Here they have what is known as a bolt. This is a bolt circle right here. Okay, it's got a pattern hole on a bolt circle. There's the bolt circle. It's in basic size, so it's theoretically exact, 2.125. The angle for each hole is 45 degrees, and that is theoretically exact when it's inspected because it has a box around it. So we're not going to check the bolt circle. We're not checking the angularity, but if you come down here, we're checking the true position of that hole. Okay, and there's 8 of them. First of all, the hole has to be 210 plus 5 minus nothing. If it doesn't meet that condition, then the part's no good. But once it does meet that, then you check the true position. It has a 5/1000ths dimensional tolerance at MMC, and they're putting on datum A and C. And C is going to be at MMC. So they would use some type of a gauge and make it here on datum C to inspect the hole pattern. See, this is how the part is going to be used in its functional environment. That's why you inspect it this way. And of course, these all are going to be based on this. This is the whole premise of GD&T. You're going to learn these symbols. And basically, we're just going to do symbol identification for this activity, for this course. But it's all in accordance with the ASME, American Society of Mechanical Engineers, the Y 14.5. The M stands for metric, and we are in, the upgrade is at 2009 was the last standard upgrade. All right. I don't know what year this was, but again, American Society of Mechanical Engineers, the Y 14.5, M is a metric, but they do have, it is used for English units as well. And 2009 was the last upgrade. So that's a little bit of background on GD&T. Next video, we're going to look at the symbols.